So welcome back for the last talk this morning. So I'm pleased to introduce Shapiro from Edinburgh, if I understand correctly, who will speak around character varieties in 60 minutes. Enjoy.
Thanks so much. It's a pleasure to give a talk here. And I have 3 warnings before I start. So first, I changed the title. It was in 15 minutes, but then Peter asked me what we're gonna do with the last 10.
I assume you just tell Russian jokes.
I could do that. Right? So that's one. The second, there will be a few top algebras and some quantized resolutions appearing at some point. You've probably already seen them in the Pavel's talk yesterday. So I just want to give a warning. Nothing is derived here, and let's pretend we don't know this word for the next hour. And the last one is I'm gonna talk about some project that we're working on with David and Grosse. And the project is somehow trying to explain there's some cross-pollination, or should be at least, between cluster take on character varieties and factorization homology take on character varieties. And I definitely come from a cluster side, so I will have to speak about factorization homology a bit. So I'll have to say a word, category, which is worse. I'll have to put some adjectives in front of it. And if you think I'm putting not really correct adjectives and they should be altered, you're probably right. You're welcome to ask questions, but I'll use audience participation in answering them. Okay, so all right. So let me we'll start with just speaking about what kind of character varieties you might want to consider. So you start with S, which is an oriented surface, and possibly you want it to have a boundary. And then you also fix a Lie group, but let's just for concreteness say it's a simple complex Lie group. As Gus said, nothing is better than semicircle. And then one way to define character variety is you just say that it's set of or space of homomorphisms from the fundamental group of your surface to G, and then you model out by conjugation, by a joint action of G, right? Well, again, it shouldn't call the variety, right? Because the action of G is not free, so it's really a stack. And I'll leave it as is now, so I'll still refer to this character variety. Now, you might want to actually make action of G free, and for that you can introduce something that people call framing. So introduce framing. Sorry, actually, before I do that, let me give an example. For example, say surface is a cylinder, or if you wish a punctured disk, then clearly your character variety is just G mod a joint action of G. Right? Well, because pi 1 is just Z, so it has one generator. Just tell where the generator goes, so G mod at G. Okay, now you might want to introduce framing. And that means that you're picking a region, a connected region on the boundary of the surface, and trivialize your G bundle there. So again, an example. So the same disk, but now I'm picking a region, so I'll put this in a small label here. Just pick this region on the boundary. Now what is the character variety now? So what data do you have? You have to fix an element of G over here, but also you have to tell where the generator of pi 1 goes, right? So now it's G cross G mod G, which is actually just isomorphic to G. Now what is this action? Well, So there's two elements of the group, F and G, right? So F is something that belongs to here, and G is something that you assign to this monodromy, G. Taking F, G, and you act by H, so how does H act? It's just right action on F and conjugation on. So you can sort of use all the action of G just to bring F to identity, and then you have just G, okay? Okay, finally, you want to consider the following thing. You want to consider decorated surface. So that means that we'll have a surface S plus marked points on the boundary. And instead of just considering a geological system, what you consider is what people call reduction to Borel. But that just means that it's still geological system plus flat section of associated G mod B, or something that's convenient actually with G mod N bundle on every component of your boundary without mark points. Let me just once again give an example. So it's the same. I'm going to take the same disk, puncture disk. But instead of one framing, I'll introduce two marked points. So that over here, well, now what's a flat section of a flat bundle? Well, just a flag. So I have a flag over here. Let's call it F1. I have a flag over here, F2. I have a flag on this boundary component. I'll call it F0. I have an element corresponding to the generator of the phi1, G. So it's in this case, I'm going to call character variety with a different symbol, because this is something people use in cluster language, and this is something this guy here who is in factorization homology, that just to tell the two apart. So this guy is the following thing, right? It's a quadruple of element of G and three flags. Right? So let's say this guy lives in G, and then I'll set this guy to be just a normal flag, and these two guys to live in G mod N. With the condition that this flag is preserved by the monodromy. That's exactly the condition that we're taking a flat section. So GF not equal to.
So what is N?
Huh?
What is
Oh, sorry.
N?
Yeah, N is the uniform radical of the Borel. So if G is SLN, then B is just upper triangular matrices, and N is upper triangular matrices with ones on the back.
And why is it? Do you take N for the other two and B for?
I mean, I said I want to be agnostic about what I take. You can do either version, but let me do this. You can as well ask one of them to be in G mod B, another in G mod F. That's right. With these two guys, you can do whatever you want. Have them G mod B, or you can have them G mod F. Okay. So what does this guy look like? So this idea is similar to the following. So imagine now that I ask these two guys to be in generic position, right? Then two flags in generic position, well, it's a free, well, G acts freely on pairs of flags in generic position, and I can use my G action to kind of bring these two flags to, standard flag and the opposite to standard flag. That's not precisely true because I'm just one torus bigger than I need to be, but almost. Let's say it's similar to just the following thing, just pairs of G and F naught. So the G stabilizes the flag. And this is what people call G tilde, and it has a map to G, and just map sort of forgets the flag. And this is what people know as Grosse and Springer resolution. In particular, it resolves the input credit. Okay. So this kind of character varieties that we're gonna work with. Now, what's known about them is, for example, they carry a Poisson structure. And there are many names for this Poisson structure. There's a T-abort construction, there's Goldman bracket if it's SL2, there's construction by Fock and Grosse, there's also another by Fock and Goncharov. So anyway, they all describe the same Poisson structure. And there's one thing that Gus mentioned yesterday. So Fock and Goncharov actually explained the following statement. They said that, well, really, the IGS are cluster varieties. Let me just briefly try to recap what I need from this notion with some properties. So first, another word. By the way, is it still okay if I write? Yes? No?
But not further down.
Not further down. Okay.
Thank you.
Okay. So in other words, so the first thing I want to have is that, well, H meaning the variety is covered by toric charts with low canonical Poisson bracket. Poisson bracket. So, low canonical here just means that if you have two coordinates xi and xj, the bracket is epsilon ij, xi, xj. And second, well, I need to give Bluing maps, and Bluing maps are certain or specific subtraction-free rational functions. Right. Now, why do people care about cluster varieties? Well, one reason is, well, you see, so they have this low canonical Poisson brackets. Now, as soon as you're talking about Poisson varieties, what's your hope? You say, well, I really would like to have global Darboux coordinate. Well, okay, the variety is going to be boring, but if you were talking about some integral system, that's fantastic, right? Global Darboux coordinate. Now, this low canonical, well, this cluster variety is sort of your best approximation to the situation when you don't have global Darboux coordinates. So this is the best approximation. So if you take logs of these guys, you'll get something constant, right? That's why they're called log canonical, but should really be log constant. But also, if you have this cluster structure, there's a kind of very nice and short theorem that you cannot find anything. You don't have an algebraic change of coordinates that actually makes it, instead of being quadratic, linear or constant and so on, right? So it's your best bet in the situation you don't really have Darboux coordinates. Other things, well, these things are super easy to quantize. You just replace this thing by few computation relations. They have some canonical family of representations, everything that got discussed. Right? Another question you might ask is, okay, well, fine, fantastic structure, but do we really have examples of it? Well, answer is yes, you do. For example, all the character varieties and all the quantizations thereof. So things like quantum group, it's duals, doubles, Borels, all these kind of constructions are there. Another, so this next sentence I'm just saying because I have a note to brag a little. So another class of examples is this. There's conjecture by Gayotto that K-theoretic column branches for 3D in n equal 4, whatever this means, gauge theories are in fact cluster varieties, and indeed there's some theorem in progress by Gus and myself that for quiver gauge theories this is actually true. There's another huge list of examples, which in particular includes things like Slodovich slices and their quantizations, spherical Dahas, which again sort of appeared here, and so on, right? So it's an interesting class of things. Okay. Now, let me also say, one thing about character varieties. So, what I sort of just told you, I told that if you start with a surface, well, marked surface, what we put hat for, the sort of being marked, and the group G will produce the following thing, right? Will produce some quantized character variety, something. Then we'll produce some family of representations. Right? So this is quantized character variety. These guys are Hilbert spaces. And, well, in fact, these guys are not just Hilbert spaces, but there's the following structure. So there's an so these guys are representations of this algebra, but moreover, they're representations of this algebra in the category of representations of the mapping class group. So there is an action of the mapping class group of the surface on this algebra. And moreover, there's the semi-direct product acts on this. Okay. Now, why would you want to have such a construction? Well, so far, no reason, but let me formulate a conjecture about it.
Can I just make sure I understand what's going on?
Yeah.
So this quantized character variety, in practice, is actually some sort of algebra.
Yeah, exactly.
So the point is, like, before I had coordinate charts that I could glue to form an actual space. I had to form the equations, all I get to glue together to form the surface, right? Is that
Yeah, that's exactly right. You just quantize them chart by chart, and then you can glue those. Well, in fact, you get an algebra with a bunch of localizations coming from different charts. That's exactly right. Okay, so why would anyone want such a construction? Or for the following reason, there's this thing called modular function conjecture. Yeah, I'm just going to formulate it in the way Fock and Goncharov formulated it. So, well, so you have a surface. And non-trivial genus, some boundary components, maybe some arc points on it. Then you choose some cycle on which you want to cut the surface. And this whole thing is your surface, but this part I'm going to call S1, and this part I'm going to call S2. For each of the surfaces, you have such a construction. The conjecture says the following, that you can take your Hilbert space coming from the big surface and actually decompose it into a direct integral over all possible values of a parameter of this representation. So what I just said, I said, well, these guys here, they just label central characters. When I cut the surface, I get another puncture, and from this puncture, I get another piece of center of your algebra. Right? Now I'm saying, well, if you took representation coming from the big surface, it decomposes as a direct integral of two representations coming from this part of the surface and that part of the surface. We'll have another piece of spectral parameter of central character, which is this nu, and I take a direct integral with respect to a certain measure on nu, and this decomposition is as this, well, okay, I'm just going to say the word as this thing for S1 tensor in other tensor product for S2 bimodule. Okay, so that's a conjecture. Well, in fact, the theorem by again Grosse and myself. This is true for G being SLN. And again, why would you want such a structure? Well, because that's sort of first step towards constructing three-manifold invariants. I'm not claiming that just given that you can have three-manifold invariants, but provided you can take traces, which you cannot really in Hilbert spaces and so on and so forth. But that's a good start. Okay. Cool.
How do you express the measure?
That's a it's called skein measure. It involves some hyperbolic signs. I don't really want to write it down. Okay. So at least maybe I convinced you that there's something to cluster varieties. Right? I want to also warn you a little bit. So what's the problem with cluster varieties? Well, for example, we obviously started from something not affine, and then I just said, okay, I covered this with charts, glued something into an affine variety. If I just would take the global algebra function and quantize it, right? So it's not precisely clear what this guy actually quantizes, right? Because it definitely quantizes something affine. So what is exactly this object? And moreover, the way people in cluster algebra construct varieties, they do this. Well, say, okay, so let's start with one chart, and then this chart has some coordinates, and you can do this thing called mutate at a coordinate. So you have, given a chart, you have a neighboring chart, and this neighboring chart, you have as many neighboring charts as the dimension of your variety. So for each coordinate, you can just go to a neighboring chart along the dimension of this direction of this coordinate. Right? Now, so basically, you start with one chart, and then you can start mutating, and at the end of the day, you have what's called a regular tree of fixed rank. So you have infinite amount of charts, and you somehow glue them together. And even if you started with a chart on your character variety, and in fact, in this construction, you start with one chart on the character variety, and you get this tree of charts. Many of them lie in the character variety, but most of them don't. So you glue something that is definitely related to your character variety, but a priori you don't know how. Okay? So that's the downside of this whole story. Okay.
So it's a priori birational to the character variety, but it's not.
It is, but in fact, like every chart is birational to character variety. But
It's
yeah,
not a subset.
yeah, birational just very mild condition. But yeah, priori is not going to stop it. Now, I'm gonna talk about factorization homology a little bit. So stepping out of my comfort zone. Before I do that, I want to point out that this is what you should think of as excision property in the future. Okay, so I can do a different thing. You can do factorization homology. And well, I'm just gonna follow the setup of there's Ben-Zvi, there's Brochier, and there's Jordan. So what do they say? They say, well, let's start with some balanced tensor category. And well, when I say balanced, I mean braided with some ribbon elements or some conditions. Now, if you don't want to know anything about braided balanced tensor categories, I am completely with you, but let's just have an example. So we take finite dimensional representations of the quantum group. Okay, we know that it's tensor, we know that it's braided. Now what's this balancing condition? Well, this balancing comes from the action of the longest element of the Lustigs group on your quantum group. So balancing comes from longest element of the Lustigs group. And well, there's a theorem due to these authors I'd like to quote. Again, I really hope that I could make all the adjectives correct. So theorem tells the following. So if you just, you know, can absorb everything that Hero told us in the last 3 days. Factorization homology gives a functor from a category of orientable manifolds And okay, I understand what orientable manifolds are. I don't understand what the categories are. But at least here's one thing that formula that everyone can probably understand, that if you start with a surface S and you provide some category that, well, just going to write the note this way, oriented. This guy over here comes with a distinguished object. Right? So there's a distinguished object inside this category coming from just inclusion of an empty surface into surface S. So plus, there's an action of Latin class group on the category. Okay, that's part one. No, sorry, I'm going to write parts 2 and 3 on the other side. So, part 2, so okay, part 1, okay, I had this 3 different versions of character varieties. So, first I had something without any framing, perfect, that part 1 completely applies. Now, suppose I have a framing. Then, part 2 tells you the following thing. So, if S has a framing, or, well, sorry, maybe framing is not the right way. S has a connected marked region on the boundary, then you have the following statement. So there exists an algebra object in that category. This algebra object is internal endomorphins inside your category of a distinguished object. So that lives inside our category. I'll tell what this internal endomorphins are in a second. And, which is the most fantastic part, is that, well, you have an isomorphism between, well, that category and the category of modules of this guy. So, yeah, by the way, this distinguished object, of course, depends on both category and surface. I just need for brevity. Right, so not only they construct a category, but also they said, well, it's really a category of modules for certain algebra. Now, you maybe make a brief reminder of what this.
What is the second subscript?
Just it's modules in the what?
Oh,
In the category.
So you're using presentability here to write the endomorphism algebra as an object of the category?
You're right.
That was a question mark. You are? Yes, okay.
Excellent question. Okay, now let me brag again and show you that I learned something about categories just a little bit, and I'm going to give a definition of what this guy is, because that was a hard time for me. So, sort of, and also define some full reminder. Right, so here's what you do. So suppose M is a module category for some other category A. What does that mean? Well, it just means that you have a functor from A box M to M, and if you take these 2 elements A and then from here, 2 objects, sorry, and then from here I send them to A tensor M. Now, what does it mean? So now choose some element M in this module category, and then you have a functor that we're going to call act M. So now it's a functor from A to M. So what it does, it takes an object from A, sends it to, well, A tensor M. So far, so good. Now we have I didn't do my homework, right adjoint. Yeah, okay, great. So now we have right adjoint to this act M. And finally, this internal endomorphisms of M is by definition, you take, let's write a joint and you add on element M, which is the same as you take this right adjoint and apply it to actually your functor xm to the one in A. Okay, and the same for internal forms. Okay, cool. So far, so good. I hope. Let me just to the third part of this theorem. So now what do we have? We started from the surface and some bound tensor category. We first produced some category out of this input, but then also produced some algebra. Now you can ask, what does this algebra have to do with the Poisson structures? We know there are character varieties, and that's exactly the third part of the theorem. So this algebra, which I'm gonna denote AS. So again, this internal homomorphism of the distinguished object quantizes Poisson structures on character varieties. Okay.
Are there particular choices of A that gives this a little bit more meaning?
Sorry?
What do you mean by quantizes?
Oh, well, I mean, you can take a character variety, you can take a saffinization,
Yeah.
it's still a Poisson variety. Now you can take its global algebra functions, and that's a Poisson algebra. It's a commutative algebra with Poisson bracket on. And now you might want to consider a non-commutative algebra, depending now not over, say, C, but over formal power series in H bar over like both C. So that in the
Maybe my question is, can you give a correspondence between choices of group G and choices of category A?
it's group A.
What is refugee?
Right, just refugee is a fine dimensional model. So for A, just a fine dimensional, sorry, yeah. Fine dimensional representation of VPG. Right? Okay. So any questions so far?
What does it mean for this algebra object to quantize? Sounds strange.
Well, that's in particular, that's an algebra, right?
So there's a forgetful functor from refugee. Refugee is a particular, every object of refugee is a particular vector space. So if you
Well,
say
I thought this was an object of that factorization homology.
Oh, so actually you have
No.
a typo. It should be, you mean in,
Oh.
you mean in A.
Yeah.
The penultimate
Not in
line
the
to the
integral,
right.
but yeah, sorry. Yeah.
Oh,
It's an
okay.
algebra
Sorry.
in A.
Okay.
Okay, thanks. Sorry.
But there does exist such a thing in, like, one might call that the underlying, but there is an underlying version in the category called factorization homology by presentability. If I have a
It
closed,
should be in A.
like, if I have a closed symmetric monoid,
That guy's not.
S is not
That guy's
a
not
closed
monoidal
symmetric
anymore.
Okay, cool. That's definitely the wrong place to ask for questions. Let me give you a couple of examples. Now, well, yeah. So before I give examples, so what happened so far? We have two constructions of these quantized character varieties, and one is very nice and natural, and another is very technical. And which one is which very much depends on who you speak to. So I come from cluster people, and but obviously I'm a minority here, so I'll try to can explain why you shouldn't hate this cluster construction by trying to reconstruct it from the point of view of factorization homology. But before I do that, let me also just focus on this algebra for a second and give you a couple examples. Maybe I'll convince you that cluster story can tell you something that factorization homology, at least a priori, doesn't. So, for example, well, A is, just a reminder, A is finite dimensional QG modules, and will be for the rest of the talk. And then, so first you can do the following thing. You can take this disk with some trivialization of your bundle in this region, and then you can ask, well, what is this algebra? Right? And the answer is, this algebra is this locally finite part of the quantum group, which we've already seen yesterday, which was called slightly differently. I think you've seen it as quantized algebra functions on G, which is a reflection equation algebra. And just again to maybe some people know it under a different name. So this guy here quantizes Semyon-Extension Poisson structure on the group G. Okay, cool. So I'll have a second example. Example number 2 is when your surface is this punctured disk with 2 more points on the boundary, and then you can ask, what is this quantization of this character variety, but in this cluster procedure? And the answer is that this guy is really just the quantum group itself, or well, in fact, it's even Drinfeld double of the quantum Borel. So even slightly nicer. So what's the difference between these two guys? Well, this local finite part is an associative algebra inside UQG, but it's not a Hopf algebra. So this guy is Hopf. This guy is associative, but not Hopf. Right? So if you want to think about in terms of representation theory, what these two different stories tell you, well, the factorization homology, at least a priori, from this nice picture, tells you something about representations of the local finite part, whereas cluster story maybe can tell you something about the quantum group, right? And in particular, the succession property you can treat as well, if you choose your surfaces right, you can treat as Clebsch-Gordon map for just the composite standard product of two representations. Okay, so now let me try to build up to this cluster setup from factorization homology point of view. Okay. Any questions now? I can answer both. Okay.
So you said that Drinfeld double is better than the QG?
Well, it is slightly, yes. You mean in what sense?
I don't know. You said,
Yeah. Well,
so,
sure, because, well, I mean, what is UQG, right? It's just quotient of the Drinfeld double by 12.
okay, this is the relative Drinfeld double. This is talking about relative Drinfeld double versus the absolute Drinfeld double.
I think he's saying you wrote, in fact, DUQB, but then you should have written UQG tensor UQT or something.
Yeah.
You meant to add some extra generators, I guess.
Well, right. I mean, I'm just so sorry. What Schrader presents is just saying that, well, this is a nice way to tell it, but this is false. The right way to tell it is actually Drinfeld double of UQB. But if you do some extra, minuscule amount of extra work, you get actually UQB.
Sorry, that says LF and stands for locally finite. So.
Yeah, local finite. Yeah. Okay, so what was the cluster story, right? Let's explain. To start doing something, we need to start with triangles, right? So we have a surface, we have marked points, we take a triangulation. So what's now if we talk about factorization homology, we don't. So sorry, triangle in this world just means a disk with 3 marked points on the boundary. Now, if you talk about factorization homology, you don't want to talk about triangulated surfaces, but you can talk about stratified surfaces. So just having 1 point is perfectly fine, and that's what I'm going to do. So building block so for clusters, this is this with 3 marked points. And what is this Poisson point corresponds to? It corresponds to G mod n cube mod G. Because you put a flag, well, again, we can be agnostic about whether it's G mod n or G mod D, but you put a flag at each of these components, your pi1 is trivial, so you just product of three flag varieties. Mod G, then you take invariant, you quantize, fantastic. In the process, you get this local Poisson bracket. Now, what's the building block for factorization homology? Well, really, I'm just going to start with a discrete one-mark point, but I said I rather want stratified spaces, so replace this guy with the following picture. So it will be disk with region marked G, region marked T, and B that's on the boundary between these two disks. And now I'll tell what I assigned to these things. And as usual, I just follow the tradition, and at the most interesting place I'll go all the way to that part of the block. Okay, so to that disk, and I'm going to call it, let me redraw it. We'll call it D1. Again, we have G, T, and B. And to this disk, I want to assign a certain category. And this category will be rep QB, which is just a name for, let me double check, it's an integrable UQB modules. With diagonalizing action of the carton. But in fact, this picture kind of hints on slightly more information than just this category. It actually also hints you on some central structure you have in this category. So also there is central structure. The central structure is as follows. So in fact, you have a functor from rep QB box rep QT, where rep Q, sorry, G, thank you, box rep QT to rep QB. And just on the level of object, what it does, it takes, say, V chi. So V encodes representation of G, chi is just a little character which encodes representation of T. Sends it to restriction of, well, or maybe better, forgetful function. From you just forget it to a representation of UQB, then you induce from a representation of UQB from the character. So induction on this guy. Okay. And well, when I say central structure, I also need to explain how I swap places of the object, of the tensor product here. And well, this guy has an R matrix, which also induces some R matrix on here. So these guys are braided tensor categories, and I can actually construct also a I forget what it's called. What is this guy?
Half braiding.
Huh?
Half
Half braiding.
braiding.
Yeah, half braiding over here. Just don't want to write the formula because I'll never use it again. Okay, fantastic. Now.
Reduce this from T to B, and that's integrable induction, so it doesn't change anything. Is it still running?
Right, I mean, exactly. So just all your E generators just act as zero. So it's a boring motion.
It's just scaling by characters.
Sorry?
Just scaling by characters.
Yeah. Okay, now let me just claim some results of some calculations. So what I just told you, well that the thing I want factorization homology to assign to this feature will be just by definition rep QB. Now, well, here I have distinguished object which corresponds to embedding of an empty surface. Well, this guy just equals to trivial representation inside here. But now you can ask, well, what is this algebra that we're getting? And if you take internal endomorphisms, and I'm gonna put internal endomorphisms with a subscript. Subscript will be G cross T, which just means that still I've taken internal endomorphism, but I still have a rep G box rep T action on that guy. So internal endomorphisms of this distinguished object corresponding to G1. This guy is again it's calculation, it's just OQ G mod n plus some quantization of well, one way to think about it is quantization of Poisson structure in G mod n, another is you take OQG and you take an n there.
I forgot your notation is ZQ.
I actually never said it. So this is the name of the function. This is what factorization homology assigns to. Okay. Now, so far so good. What we did was that I described a category that we assigned to this with 1 mark point. I described this algebra that we get from this category. Now we're almost done. Let me just show what happens when you have 2 points and then 3, 4, and well, we still have about 20 minutes to go.
Sorry, when you put G mod n instead of G, is there anything commutative about that?
Sorry.
Is there anything commutative about OQ G mod n?
No. This is well. I mean, think of G is just SLN, and then it's just the upper triangular matches with ones on the diagonal. So, well, I mean, you can take algebra functions on this guy. It's going to be Poisson algebra. Well, I mean, you can because it's not defined. But assume you can. When you Poisson algebra, you quantize it. It's not going to be commutative at all.
How does this play with the fact that it seems like V1 has a monoidal structure called stacked vertically? You're taking a unit.
That's an excellent question.
And the morphisms of that, the commutative object?
It's braided commutative. He's not going to use this, but it is a braided commutative. He's also about to explain that it's not an equivalence. Unlike in our paper, this rep QB is not equivalent to that. So.
Okay.
I think so.
Cool. Right. So we'll describe this with 1 point, but this with 2 points. Well, I mean, we just use what factorization homology tells you. It tells you that well, if you have this with 2 regions. Sorry. This with 2 regions, you have T over here, and T over here, and G over here. Well, what factorization homology tells you is that VQ of this disk with 2 more points. This is simply the same, or well, the same as VQD1, both VQD1 over VQD. I don't have a notation for it, but D0. So with 0 mark point, it's a disk which is colored G. The whole of it is just colored with G. Or equivalently, you can say that this is rep QD. Box rep Q the opposite over rep QG. Right. And I can say, well, again, what's the distinguished object there? So I can still write here. So distinguished object in this with 2 mark point will be. Sorry, let me write away just double the algebra. Internal endomorphisms. Now with the action of G cross T with the distinguished object in this 2 mark points. Right? This guy here is again it's some relatively easy calculation. It's just OQ G mod n tensor OQ G mod n, but you have to take this graded tensor product. In other words, relations between these 2 parts of OQ G mod n are given by some kind of what people know as RLL type relations. It's relations involving Canard metric. Well, I'm not going to explain what happens when you replace 2 by 3, 4, and so on, but you can probably guess. Okay, so now D3 is really this factorization homology replacement for a triangle in this cluster story. Now, you also in the cluster story you also have to glue triangles, and that's also absolutely clear what happens. So the limit of triangles. You have this D4s or 4 windows, 4 marked points. So these guys are colored T. These guys colored G. And you can cut it this way. And what it tells you is just that ZQ of D4 is just isomorphic to ZQ D3, both ZQ D3 over ZQ D2. Okay. Now I'm dreaded to do that, but it's kind of, I'm going to get sort of logically just move a little bit from what I was saying. So are there any questions?
So I'd like to understand the example of the annulus. I know that's not a stable example, but that is annulus with no triangulation whatsoever. Whatever the correct answer to that is it the T category, the Hochschild homology of the T category tensored over Hochschild homology of the G category?
David, that's all right. I really need your help here.
If I have an annulus with no triangulation whatsoever, I know that's an unstable thing, but is the correct answer just the Hochschild homology of the T category tensored with itself but over Hochschild homology of the G category?
If you have no T markings at all?
Sorry, so I'm imagining that in this picture, like, oh, I see what you're saying. Right, so I should have T markings to be able to say what I'm saying.
Well, there's a statement without G markings at all, which is in our paper, that the Hochschild homology of the braided tensor category computes the annulus, and that's, well, it's obvious, I guess.
Yeah.
There is a related statement if you put in T markings. Maybe we can discuss that.
Okay, I'm not going to ask more questions. You can talk with David. Okay, so far I just explained you. Do you have what 7 more minutes?
Yes.
Okay. So far I explained you some construction. Let me actually, well, and also maybe a couple of simple calculations. But let me state a theorem. There should be at least one here. Let me kind of go back to this, to the case of surfaces without any markings, and explain something about this setup first. So here's what was happening when you didn't have markings. So you had no markings, or I'll just call it the setup of David and Adrian. You had a function of global sections, just the internal combs from distinguished object to whatever, was a function that took you from ZQS to modules over that algebra, the morphisms, for G, the distinguished object. And this function was actually an equivalence. And one way to think why it was an equivalence was because you were quantizing quadrature sheaves on something affine. Now, what you could do then, you could try to take G invariant to get into this, the morphism of this G invariant module. And this guy is not an equivalence. Well, partially because because it's not conservative, and this is because G doesn't act freely. Okay. Now let's see what happens when we have markings. I'm gonna once again go over there. So now this guy is marked surface. You have the same story. So you have functors from the factorization homology of the marked surface to endomorphins in this rep G equals T to the n, where just n is the number of markings you have in a surface total of distinguished object that you assign to the surface with modules. But this guy is not an equivalence anymore. The reason it's not an equivalence because even if we just take this with 1 mark point, it's G mod n, it's not affine, right? So you kind of hope that this guy is an equivalence. Then you're going to once again try to take G invariance, and as before, this is not an equivalence either. Right? So, but again, what kind of naive geometry tells us? It tells us, well, yeah, okay, we're working with something non-affine, but at least we can take charts. And charts, for what we know, these cluster charts should be affine, right? They're just you just C star to the dimension. So we would like to find some localizing subcategories here that replace our cluster charts. And we can indeed do that, but before I explain how we do that, I want to remind you that what happens if we have a triangulation for this marked surfaces. So maybe I didn't write it yet. Yeah. So over here we have a marked surface and we have a triangulation. And each edge of a triangulation gives rise to an embedding of D2 in our marked surface. Right? So fix a triangulation. I'm going to put a delta under bar of surface S with markings. Then each edge gives rise to an embedding of D2 inside S. Right? But moreover, let's recall what this D2 was, right? So recall that if you take internal isomorphisms of this distinguished object in D2, what this algebra was, well, it was just OQ G mod n and rho Q G mod n. And you can look for G invariance inside here, and if G is SL2, then there exists unique G invariant, which we call AE. E for the H, A for invariant. So if we go to high rank, there's no problem as well. If we just have more of those, that's fine. But for now, let me just do a sort of, because it's easier. We just have a unique function. Each edge gives us a function. And here's finally a theorem I want to claim. Before I claim a theorem, let me actually draw something here. So I can take the same guy. This is an algebra, and I can now localize this guy at this AE, where E varies over my triangulation. Take models of that. Right? So, well, this is a localizing subcategory. ZQ is a localizing subcategory of this guy. That's a statement, but it's not too hard. This guy is an obviously localizing subcategory as well. And I'm going to just draw it here, but actually localizing subcategory of this guy. Right? So this is localizing. Okay, so what I just told that, well, okay, we don't have really great control of this category at the moment, but at least we found sort of localizing categories that are modules for some algebra that give us a way to understand what's going on here, sort of to test everything against this case. But moreover, you can take G invariance, and now this also becomes right with the end equivalence, and this is a theorem due to Ian, David, Gus, and myself. Am I out of time? Okay, so let me.
Cluster.
Huh?
I think you didn't say out loud that that is a cluster.
Ah, sorry. Yeah, and this. Okay, yeah. I mean, what's the relation with this cluster thing? That well, these guys are really just cluster variables for a SL2 character array. Now, what should the takeaway be? Let me formulate just one last conjecture, and then I'll stop. Conjecture is as follows. You can also, so we outline the relation between this guy and these guys. Okay, so this is just a quantization diversion of cluster charts. Now, what is the relation between this guy and this guy over here? Conjecture that that guy without any quantization is actually just a limit of those localized guys. And what's one way to understand this conjecture? Just tells you that really your cluster charts cover character variety, quote unquote, up to codimension 2. Now, what is this character variety? Well, this thing is really just a factorization version of, or category version of, affinization of a character variety. So in particular, this whole story tells you A, one way to understand cluster charts is localizing subcategories for this guy here. B, what cluster people are talking about. They're really talking about affinization of character stacks.